In this video, I'm going to go over the addition and subtraction formulas in trigonometry. We have 6 addition and subtraction formulas: an addition and subtraction formula for sine, an addition and subtraction formula for cosine, and addition and subtraction formula for tangent. So I'm going to use these 6 formulas to solve a wide range of examples. Starting with the first example, let us find the exact values of cosine of 75 degrees and of sine of pi over 12 radians. So to find the cosine of 75 degrees, first we write 75 degrees as the sum or difference of angles whose cosine we know. So we can write 75 degrees as the sum of 30 degrees and 45 degrees. So cosine of 75 degrees, that's cosine of 30 plus 45 degrees. Now we use the addition formula for cosine to figure out the exact value of cosine of 75 degrees. Cosine of 30 plus 45 is cosine 30 times cosine of 45 plus, actually minus, sine of 30 times sine of 45. Notice there's a minus sign because if we go back, if you look at the addition formula for cosine, notice that cosine of u plus v is cosine u times cosine v minus sine u sine v. That's why I put a minus in the middle. So cosine of 30 is root 3 over 2. Cosine of 45 degrees is root 2 over 2 minus sine of 30 degrees is 1/2 times sine of 45 degrees, which is root 2 over 2. Root 3 times root 2 is root 6 minus 1 times root 2 is root 2 divided by 2 times 2. Notice the denominators are the same, that's why I combined the numerators. That's divided by 4. So the exact value of cosine of 75 degrees is precisely root 6 minus root 2, all divided by 4. Next, let's find the exact value of sine pi over 12 radians. Now, if you convert pi over 12 radians to degrees, you'll see that it's 15 degrees. Pi over 12 radians is 15 degrees, so we can write 15 degrees as 45 degrees minus 30 degrees. In other words, we can rewrite sine of pi over 12 radians as sine of 45 degrees, which is pi over 4 radians, minus 30 degrees, which is pi over 6 radians. And you can check that if you do pi over 4 minus pi over 6, you'll get exactly pi over 12. Now we use the difference formula or the subtraction formula for sine. That's going to be sine of pi over 4 times cosine of pi over 6 minus sine of pi over 6 times cosine of pi over 4. Sine of pi over 4 is root 2 over 2. Cosine of pi over 6 is root 3 over 2 minus sine of pi over 6, that's 1/2, times cosine of pi over 4, which is root 2 over 2. Combining, we get root 6 minus root 2 divided by 4, which notice the exact answer we got for cosine of 75 degrees. And that's not surprising because 75 degrees and 15 degrees are complementary angles. They add up to 90 degrees. So the cosine of one of them will equal to the sine of the other, and vice versa. That's why we got the same answer for both problems. Next, let's find the exact value of cosine of u plus v, given that sine u is 12 over 13, and u is between 0 and pi over 2 strictly, so u is an acute angle, and cosine v is minus 3 over 5, and v is an obtuse angle. It's strictly between pi over 2 and pi. So let's write the addition formula for cosine of u plus v. Cosine u plus v is cosine u times cosine v minus sine u times sine v. Now note that we know what sine u is, we know what cosine v is, but we don't know anything about cosine u, and we don't know anything about sine v. So let's go ahead and figure those out. Let's draw the pictures. We have first, let's deal with the angle u. So we know u is an acute angle, so it's got to lie in the first quadrant. We know the sine of u is 12 over 13, which we know in a right triangle is the opposite over the hypotenuse. So we have an opposite side of 12, the hypotenuse is 13, and u is an acute angle. So we got something like this. The opposite is 12, hypotenuse is 13. Here's angle u. As you can see, it's an acute angle. Now, using the Pythagorean theorem, you will see that the adjacent side to u would be 5. What do we need from this triangle? We need cosine u. Now, cosine u is the adjacent over the hypotenuse, which is 5 over 13. So now we know cosine u is 5 over 13. Next, let's figure out sine v. So we need the picture for angle v. So here's the x and y axes. V is an obtuse angle, so it's got to lie in the second quadrant. What do we know? We know that cosine of v is minus 3 over 5. And this is really the the adjacent over the hypotenuse in the following right triangle. So in the picture, here's u, which is here's v, which is an obtuse angle. So when we create the right triangle, we're essentially looking at the reference angle to v. Here is the reference angle to v, which is the acute angle between the horizontal axis, or the x-axis, and the terminal side of v. So in this triangle, we know the adjacent is 3. We know the hypotenuse is 5. And using the Pythagorean theorem, this leaves us with the opposite side being 4. So what do we need from this triangle? We need sine v. Sine v is the opposite divided by the hypotenuse, which is 4 over 5. We have everything we need, so let's figure out cosine of u plus v. That is cosine of u, which is 5 over 13, times cosine of v, which is minus 3 over 5, minus sine of u, which is 12 over 13, times sine of v, which is 4 over 5. Notice the denominators are equal. 13 times 5 is 65. And minus 15 minus 12 times 4, that's minus 15 minus 48, which equals negative 63. So cosine of u plus v is minus 63 divided by 65. Next, let's look at the expression sine of arctangent 1 plus arc cosine x and write that as a purely algebraic expression in x. So this means when all is said and done and write our final answer, there should be no trigonometry whatsoever. So to start this problem, I'm going to start out by calling arctangent 1 u. I'm going to call arc cosine x v. So we'll say u is arc tan 1, which means if we apply tan on both sides, we get that tangent of u is equal to 1. Well, we can write that as 1 over 1, which, remember, in a right triangle, the tangent is the opposite over the adjacent. So here we have a right triangle where the adjacent is 1, the opposite is 1, and here is angle u. So this is a right isosceles triangle with legs of side length 1. Using the Pythagorean theorem, we'll see that the hypotenuse is square root of 2. Let's move on to v equals arc cosine x. If we apply cosine on both sides, we'll get cosine v is x, which is x over 1. In a right triangle, the cosine is the adjacent over the hypotenuse. So this gives rise to a right triangle whose adjacent is x. The hypotenuse is 1, and here you can see angle v. Using the Pythagorean theorem, we see that the opposite side would be square root of 1 minus x squared. You can check that that's true. Now, let's see what we need here. Let's go back to our original expression, sine of arctangent 1 plus arc cosine x. Well, this is sine of u plus v. Using the addition formula for sine, this is sine u cosine v plus sine v cosine u. What do we need? Sine u, let's write it here, sine u in this triangle is the opposite divided by the hypotenuse, so this is 1 over root 2. So we'll write 1 over root 2 times cosine v. Well, cosine v, we need the second triangle, cosine V is the adjacent divided by the hypotenuse, so this is none other than x, plus, next we need sine V, so we need the second triangle. What is sine V? It's the opposite divided by the hypotenuse, so this is square root of 1 minus x squared. Times cosine U, for that we use the first triangle. Cosine U is the adjacent divided by the hypotenuse, which is 1 over root 2. We have our final expression for sine arctangent 1 plus arc cosine x. Let's rewrite that. Sine arctan 1 plus arc cosine x is 1 over root 2x plus 1 over root 2 times square root 1 minus x squared. We can write that in compact form as x plus square root 1 minus x squared divided by the square root of 2. Notice this final answer contains no trigonometry whatsoever, which was the original point of the problem. We would like to write sine of arctan 1 plus arc cosine x purely in algebraic form. Next example, let's prove the cofunction identity that cosine of pi over 2 minus x equals sine x. So to prove this identity, I'm going to start with the left-hand side of the presumed identity and show that it's equal to the right side, namely to sine x. So I'm going to start with cosine of pi over 2 minus x, and I'm going to use the subtraction formula for cosine and proceed from there. So this is equal to cosine pi over 2 times cosine x plus sine pi over 2 times sine x. Cosine pi over 2 is 0 times cosine x plus sine pi over 2 is 1 times sine x. And this leaves us with a final answer of sine x. So we showed that indeed the left-hand side equals the right-hand side. Next, let's simplify the expression tan of x minus pi over 4. For that, I'm going to use the difference formula or the subtraction formula for tangent. So, tangent of x minus pi over 4, this is tangent x minus tangent pi over 4 divided by 1 plus tangent x times tangent pi over 4. Recall that tangent pi over 4 is 1, so we have tan x minus 1 over 1 plus tan x times 1. And the final answer is tan x minus 1 over tan x plus 1. So this is a simple application of the difference formula for the tangent function. Next example, find all the solutions of sine x plus pi over 4 plus sine x minus pi over 4 equals negative 1 in the half-open interval from 0 to 2 pi. So we only want the solutions that fall into the half open interval from 0 to 2 pi. So we start out by expressing sine x plus pi over 4 in terms of the sum formula, and sine x minus pi over 4 in terms of the difference formula. So, sine x plus pi over 4 is sine x cosine pi over 4 plus sine pi over 4 cosine x. This is sine x plus pi over 4 plus. Now I'm going to write the difference formula for sine x minus pi over 4. So that's sine x cosine pi over 4 minus sine pi over 4 cosine x. So that's the left-hand side of the equation, and all of that equals -1. Now, if you look at this left-hand side, notice that sine pi over 4 times cosine x minus sine pi over 4 cosine x cancel out. And we have sine x cosine pi over 4 added to itself. So we have 2 sine x cosine pi over 4 equals -1. So 2 sine x cosine pi over 4 is root 2 over 2 equals -1. Notice the 2's cancel. So we have root 2 sine x equals -1, which means sine x equals -1 over root 2. We want all of the values for x for which sine x equals -1 over root 2. We want only the values that lie in the interval from 0 to 2 pi, the half open interval. So if we look at the unit circle, there are two values that satisfy this equation. The first value is at 5 pi over 4. Sine of 5 pi over 4 is -1 over root 2. And also 7 pi over 4, the sine of that angle is -1 over root 2. This means we have two solutions to this equation. X equals 5 pi over 4 and 7 pi over 4. These are the only two solutions in our desired interval. Half open interval from 0 to 2 pi. Finally, let's prove that if h is not equal to 0, then cosine of x plus h minus cosine x over h can be expressed as cosine x times the quotient of cosine h minus 1 over h minus sine x times the quotient sine h over h. This is useful in Calc 1 for finding the derivative of the function cosine x. So we start with the left-hand side. Cosine x plus h minus cosine x over h. I'm going to manipulate that and show you that it's indeed equal to the right-hand side. So I'm going to start out by using the sum formula for cosine x plus h. That's cosine x times cosine h minus sine x times sine h minus cosine x all divided by h. let's rearrange the terms in the numerator. We have cosine x cosine h minus cosine x minus sine x sine h, all divided by h. All I did is I swapped the last two terms. Now looking at cosine x cosine h and cosine x, we can factor out a cosine to get cosine x cosine h minus 1 minus the last term sine x sine h, all divided by h. So let me rewrite that again. We have cosine x cosine h minus 1 minus sine x sine h. Notice, going back, all of this is divided by h, so we can split that into two fractions as cosine x times cosine h minus 1, all divided by h, minus sine x times sine h divided by h. One last step, we express our last we have our last expression as cosine x times cosine h minus 1 over h minus sine x times sine h over h, which is the desired right-hand side. Cosine x times cosine h minus 1 over h minus sine x times sine h over h, which is exactly what we did.